We're now going to talk about one of the most widely used notions in the calculus, the notion of related rates. This is used very, very often, and in particular, although not exclusively, in particular, these tend to get used in the physical sciences and even the life sciences. Suppose I have a spherical balloon, and suppose air is filled into this balloon. At the start, maybe it has 1 cubic centimeter of air. At the end, it has 10 cubic centimeters of air. Now, that's a change of 9 cubic centimeters. But the question is, how long did it take for that to happen? If I inject the air very, very slowly, then it might take an entire day to go from 1 cubic centimeter to 10. If I inject the air very quickly, it might take just a minute or maybe even a second to go from 1 cubic centimeter to 10. How fast something occurs is the rate. We're interested not only in the change, not only in the total amount of change, but how fast did that change occur? More to the point, how much time elapsed? What is the change in that case? What is the change in volume? Not just the overall change in volume, but what is the change in volume with respect to the time elapsed? Because if I'm injecting air into this balloon at 10 cubic centimeters per second, that's a significantly different occurrence than if I'm injecting air into this balloon at 10 cubic centimeters per year. That's a much slower rate, much smaller rate of change. And so rate of change has to do with not just the change, not just the delta volume, but how much volume changes with respect to change in time. And so we end up with things like this. Suppose I have the volume, and let's just pick something at random here. I have the volume of a cone. The volume of a cone is 1/3 pi r squared h. The volume of a cone is 1/3 pi r squared h. None of these geometric formulas need to be memorized by you. I will always give you the geometric formula. In practice, you have access to the internet. Look up volume of a cone. So I will play that role for you, and any geometric formula you need, I will simply give to you. There are a few things I would think you should know. I think you should know, for example, there are going to be some problems here with right triangles, and I would hope that you would know Pythagoras. I would hope that you know the basic trigonometry. Sine is opposite over hypotenuse, and so on. But any geometric formula, I will just give to you outright. So you don't need to worry about looking those up or having access to them or even having them memorized. So suppose we have a cone. This is a right circular cone. So I have a cone which has a base radius. It has a height, which is the vertical height, not the slant height. So actually h, a better picture here would be to put h to be this vertical height. And so the volume of this cone, the amount of space it occupies, is 1/3 pi r squared h. You'll recall that we talked about taking the rate of the implicit derivative of this, differentiating implicitly. But whenever we do related rates, we're always talking, when we talk about rate, it's how fast, and that implicitly, that just involves the notion of with respect to time. And so even though the variable time, t, does not appear in this equation, we will need to differentiate with respect to time. And so just as an example, I'm going to go through this example. I'm going to differentiate this with respect to time just to show. And we're going to do this first video. I'm just going to take several formulas, differentiate with respect to time, just to get used to doing that part. Once we have that, then we have pretty much a step-by-step procedure. Do this, do this, do this, do this, do this, and you're out. But the key is making sure we're sure of our footing on doing the implicit differentiation with respect to time. And so I'm going to differentiate this equation. There are how many variables here? They're not 4. Remember, pi is not a variable. Sometimes you'll see this. Sometimes you'll see this. Pi over 3 r squared h. These are the same thing. Pi over 3 and 1/3 pi are the same thing. It's just this is a constant, this is a constant. So it doesn't matter to me which of these forms you pick. I tend to use, volume is 1/3 pi r squared h. This is a constant, all right? So there are three variables. One variable is v, one variable is r, one variable is h, because there are three variables that determine the size of this cone. If h changes, so does the volume. If r changes, so does the volume. If h and r both change, potential, the volume changes. If volume changes, at least one of these needs to change. So the three variables are volume, radius, and height. And we're going to implicitly differentiate implicitly both sides of this. So the derivative of volume with respect to time is the derivative of volume with respect to time, dv dt. This is what I call a differential. I call it that because that's what it is. It's a differential. So this is the differential of volume with respect to time. So later on, we're going to be counting them, and that's what I mean by a differential. Now, on the right-hand side, we have two variables multiplied. We need the product rule. We need the product rule. So if we're doing this differentiation with respect to time, we need the product rule, and we also need to figure out which of these coefficients, which variable is the coefficient. I just stick the coefficient with the first variable. Constant multipliers multiply along. So I need first, copy, paste. I need first times derivative of the second plus second times derivative of the first. And so first times derivative of the second. What is the derivative of h? It's not just one, it's dh dt, right? The only time we wouldn't need one of these differentials is if time is actually in the equation, which it isn't and typically won't be. First times derivative of the second plus second times the derivative of the first, multiply by 2. I can write this as 2/3 pi r to the first, but then I need dr dt. First times derivative of the second plus second times the derivative of the first. You do not, in fact, I would advise against it, do not need to simplify this at all. We'll see that as we get to this. So I'm just going to take some more formulas and practice this procedure. Notice if you have two variables multiplied, you do need the quotient rule, the product rule. All right? Suppose we have x squared plus y squared equals z squared. Can you differentiate with respect to time using implicit differentiation? This should be pretty straightforward. Term, term, term. The derivative here is 2x dx dt plus 2y dy dt is equal to 2z dz dt. There, we've differentiated with respect to time. All we're doing is practicing this. Once we have this down, the rest of it is cookbook. Follow this step, 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 and you're out. All right? So, what else do we have here? Let's go, suppose we have the area is let's do the volume. Volume of a sphere is 4/3 pi r squared, cubed. The volume of a sphere is 4/3 pi r cubed. Differentiate both sides with respect to time. One variable here, one variable here. This is just constant multiplier. All right, so the derivative here, dv dt, is equal to derivative. Multiply 3. So I can write this as 4/3 pi times 3 if you want to. That's fine. You could cancel the 3's on the fly if you like. This is r to the second dr dt, and then yes, the 3's do cancel. So you don't need to simplify, but some of this obvious stuff is maybe not the worst thing in the world to do. All right? What if we have the area, surface area of the sphere? That's 4 pi r squared. That's the surface area of a sphere. Can you differentiate both sides of that? Well, dA dt is equal to 8 pi r to the first dr dt. If you can differentiate formulas, then you should be in good shape. I is equal to PRT. Differentiate with respect to time. That's probably got 3 variables. We don't want to do that for our purposes. Let's do this. Let's do tangent of theta is equal to y over 10. If you wish, you may rewrite this. This is not required, but if you wish, some students to prefer this. Write this as 1/10 y. Just leave this as coefficient. Some people prefer this, some people, they're fine both ways. I like to do this for students because I think it makes it more obvious. Differentiate both sides with respect to time. What's the derivative of tangent? Derivative of tangent is secant squared theta, but we need d theta dt, is equal to constant multipliers, multiply along. The derivative of y is dy dt. All right? So that should be very straightforward. Let's make it a little bit more elaborate here. What if we have secant, I'm sorry, let's not do secant. I've got my marker. Let's do cosine of theta is x over z, and we need to differentiate both sides of this with respect to time. So one option is we've got a quotient rule coming at us here. Luckily, we know the quotient rule. So this would be the derivative of cosine is negative sine of theta, d theta dt. Derivative here is quotient rule. It's denominator times derivative of the numerator minus numerator times derivative of denominator all over denominator squared. Denominator times derivative of the numerator minus numerator times derivative of denominator. All derivatives are with respect to time. And then divide by denominator squared. And you do not need to simplify that. In fact, it's probably better if you don't. This is certainly one option. Let me show you another option. Some students like this. You can use either way. They both give you the same final result. Is we could take this expression and rewrite it cross multiply. X times 1 is equal to z. We could rewrite this as z times cosine theta. Multiply both sides by z to clear the fraction. And then use product rule if you prefer that. If you prefer product rule to quotient rule, students always want to know which one's easier. Well, neither one. They're both about the same amount of work. It doesn't matter which one you pick, just go with it. This case, if you did this, this would be first times derivative of the second plus second times derivative of the first is equal to, so this is first times derivative of the second, negative sine of theta. Make sure this is in parenthesis. And I need, left my little, didn't leave enough space here. First times derivative of the second. Anytime you do a derivative of a variable, you need that differential. First times derivative of the second plus second times derivative of the first is equal to the derivative on this side is dx dt. It is not obvious, but any result you get from here and any result you get from here are going to be the same result. That's not obvious, but that's the same result for our work. So, given essentially any formula, you should be able to do the derivative with respect to time, no matter what variables are where, whether we use quotient rule or chain rule or product rule or the trigonometric rules, constant multiplier rules. Being able to do that needs to be part of your comfort zone. If you have that, then you should be in very good shape regarding a related race, because everything else is going to be follow this cookbook step-by-step procedure. One small detail before I leave off. Theta must be in radians. Theta must be in radians. Theta must be in radians. So if we're talking about given in revolutions, convert to radians. If you're given in degrees, it actually is best to convert to radians. Convert everything to radians. Now, in the end, let's pretend you do a problem. And you work a problem, and you work, and your final result is theta is equal to 2.17 radians per minute. Let's suppose we're going to work a problem, and that's our final result, 2.17 radians per minute. After you get your final result, you may, if you wish, you may convert this back to degrees, because we know 180 is to pi, as don't know yet, is to 2.17. So 180 is to pi, as so many degrees is to 2.17, cross multiplying. You can convert back to degrees anytime you want. But all the work that we do with this calculus, theta needs to be measured in degrees. If it's given in revolutions, convert to degrees. So convert to radians. Everything needs to be done in radians when we do the calculus with the trigonometric functions. All right? Oh, one last little bit. Let me leave you with this. Suppose we are given water is filling a tank at, let's say, 45 cubic liters per minute. 45 cubic liters, or 45 liters, let's do cubic centimeters, let's say. Cubic centimeters, or let's say 45 cubic centimeters per minute. Cubic centimeters per minute. This tells us that we're dealing with volume. Cubic centimeters measures volume. If we're saying, suppose we say the area is changing at 14 square feet per second. Suppose the area is changing at 14 square feet. Square units measure area. Cubic units measure volume. Square units measure area, cubic units measure volume. And suppose we're given the length is changing at, let's say, 10 meters per second. Meters to the first, this measures length. So if you're very careful just to look at the information you're given, it can tell you what unit you're working with. And so if I have 45 cubic centimeters, this is cubic centimeters, per minute, I know this is giving me the rate of change of volume with respect to time, because volume is cubic centimeters. I know this is giving me the rate of change of area with respect to time, because square units are area units. And I know this is giving me the change of length. So this might be change of just length with respect to time. Maybe x is some length in the picture. So this is volume because it's third power. This is area because it's second power. This is linear because it's first power. Noticing that is a really big advantage, and that can really help you understand what needs to happen in the problem.